Okay, hello again. I changed the last circuit a little bit to a little bit more complicated circuit with another capacitor here, and I wanted to show you how to draw the Bode plot and how to analyze this circuit. So first of all, what I did was finding the transfer function. And as I explained before, to find the transfer function, we just need to use basic formulas for KCL and KVL. And we also need to know the relationship between voltage and current for different devices, for different elements. So for example, for resistor, it's Ohm's law, V is equal to Ri. Capacitor, you need to know the impedance of the capacitor, it's 1 over j omega c. For inductor, it's j omega l. And so what I did here for this circuit, which is basically the modified differentiator, you can see here that what we have here is a negative feedback, and since this non-inverting pin of the op-amp is grounded, this is going to be our virtual ground. So it means that this also has zero potential, right? So then I wrote the KCL at this node, at the inverting pin of the op-amp. So the current that goes through voltage source into the inverting pin, it's going to be V in minus 0 divided by 1 over j omega c. The current that goes through this resistor, it's going to be 0 minus VO divided by 1 over R2. The other current that goes through C2, it's going to be 0 minus V out multiplied by, or divided by 1 over j omega c2. And if you simplify this, you get to this transfer function, right? If we didn't have C2, you would only get this part. You only get the numerator here, right? And you would just have 1 0, and that would be it. But by adding a C2 here, you would also have a pole in your transfer function. Okay, so one thing that I wanted to show you here is first how to find the magnitude and the phase of the transfer function. So first of all, you remember that if you have two complex numbers divided by each other, like Z1 divided by Z2, the magnitude of Z1 divided by 2 is basically the magnitude of Z1 divided by magnitude of Z2. Phase of Z1 divided by Z2 is equal to phase of Z1 minus phase of Z2. And if this was multiplication, Z1 multiplied by Z2 would be magnitude of Z1 multiplied by magnitude of Z2, and phase would be phase of Z1 plus phase of Z2. Okay, and for a complex number like C equal to A plus B times J, magnitude, it's gonna be, can you guys guess? Or can you remember? What's the magnitude of a complex number? I'm gonna move this a little bit. It's gonna be A squared plus B squared, basically square root of A squared plus B squared. And the phase of C, it's gonna be tangent inverse of B over A. Okay, so here, this is our transfer function. I wanted to find its magnitude. So the magnitude of the numerator, it's going to be omega R2C1. Basically, this is just an imaginary number. Only has the imaginary component, so it would be this part. And its denominator, it's going to be square root of 1 plus omega squared R2 squared C2 squared, right? And if I want to display the magnitude in decibel, it's going to be 20 log of this thing, and you know that log of A divided by B, it's going to be equal to log of A minus log B. So that's what I did here. I got rid of the square roots because I took it out. like this is basically 1 plus omega squared r2 squared c2 squared raised to power 1 over 2. So it comes out of the log, and the 20 times 1 over 2 becomes 10. So this is how you can find the magnitude of a transfer function. And the phase, so let me actually draw the complex plane here, right? If this is if we have a complex number a plus bj, this is that complex number. So this is going to be the magnitude, and the phase is tangent inverse of b over a, right? This is the real axis, this is the imaginary axis. So here we have negative j omega something, right? So it means that we are somewhere on the lower part of the imaginary axis. What is the phase at this part? What is the angle? This is like what I'm talking about, the phase. What is the phase? It's either 270 degrees, you can say it's under 270 degrees, or it's negative 90 degrees, right? So I put negative 90 degrees for the phase of the numerator. What is the phase of the denominator? It's tangent inverse of the imaginary part divided by real part, which is 1. So this is what we have for the phase, okay? So just wanted to show you that you can find the magnitude and the phase of a transfer function like this. The other thing I wanted to show you is how to do the Bode plot here. So for the Bode plot here, first we have to find our poles and zeros. How many poles and how many zeros do we have? Okay, so how many zero do we have? We only have 1, right? When omega is equal to 0, the numerator becomes 0. So we only have 1 0 at omega equal to 0. How about the pole? We only have 1 pole when j omega is equal to 1 over r2 c2, right? 1 over r2 c2, okay? Now, what I'm drawing here is basically first the impact. Let's just like discuss with what we know, the impact of the pole. So I'm drawing the impact of the pole in green, right, on the magnitude. If you remember, on the magnitude, the impact of the pole starts at the pole, which is, let's say like I have these values for R2, C1 and C2. So 1 over R2, C2, it's going to be 1 over 10 to power negative 4. So it's going to be 10 to power 4, right? So the impact of the pole would be nothing happening up to this point, and then it's going to go down with the slope of, what's the slope? Negative 20 dB per decade, right? So if we only had this function, then this would be our Bode plot, right? But we also have a 0. What is that 0? Where is that 0? The 0 is at omega equal to 0, right? At omega equal to 0, h of j omega